So, a summary of similarity is that polygons that have corresponding angles that are congruent, remember, congruent means equal, and corresponding sides that are proportional are similar. So, you need two things on your checklist: that the corresponding angles are equal or congruent, and that the corresponding sides are equal or proportional. Let's look at example number 1 here, where it's asking to identify the corresponding angles and then the corresponding side lengths. Now, I call this like a bow tie example, where you have these two triangles that are attached at this point. And there is a trick in trigonometry that helps us identify equal angles. Now, anytime you have an X like this in trigonometry, the opposite angles are equal. So this angle is equal to this angle, okay? So in these two triangles, these two angles would be congruent, okay? And then if you had a different shape, if you had an enclosed shape of some sort, these two angles will also be equal. Knowing that they're equal right now is not helpful in any way, but knowing that these two are equal is very helpful. Okay, so we can start by knowing that those two angles are equal. Now, to help identify the other angles or the other side lengths that are corresponding, let's look at the other angles, okay? Now, if you could separate them, if you could picture putting these two triangles maybe side by side, you would see that this angle and this angle are congruent. And then the last one, this angle and this angle are congruent. Now, this can really help us figure out which corresponding side lengths are equal, okay? Now, what I mean by that is I need to look at which side lengths are corresponding. So what side length of this triangle, so say what side of this triangle goes with which side length of this one. And it's common that students want to say that these two are corresponding, but if you look at the angles, all right, so say if we look at the angles, this side length runs from the blue angle to the green angle, but this side length runs from the blue to the red. So think about, well, where's the other blue to the green? It's down here. And so you can see now that this side length corresponds with this side length in our second triangle. Okay, and now that can help us identify the other ones. So red to blue is right here. So this side length corresponds with this side length, and then the last one. Okay, and if you think about look at these lines, I always find the easiest one to identify is this one here, right? So these two are parallel lines, and this one is always going to be the corresponding one in this kind of bow tie example. So you know the angles are opposite are equal, and these two are equal. And then you can kind of piece together the other two side lengths and angles from there. Now it's asking to write the side lengths as proportions. So we're comparing side lengths, okay? Let's compare the side lengths, okay? Now notice here in my proportion, this is called a proportion or a ratio when we write them as division statements like this. We're starting with the same one each time. So ST, TR, and RS, they all come from this larger triangle, and then all the bottom numbers or measurements come from the smaller one. And that's really important that you keep those numbers in order like that, okay? So let's start with ST and PQ, okay? So ST is right here, S to T, and it corresponds to PQ. Okay. And we're looking at the measurements. So this one is 6 and this one is 4. All right, so 6 divided by 4 would give me 1.5. Now, the first one doesn't make a big difference. It's when you're writing the other numbers, the other proportions to compare to, that it really makes a difference. So we always have to start with the same one. So here I started with line segment ST. That's in the big triangle. I have to do my next comparison starting with a side length in the big triangle. All right, so let's change colors and let's look at TR and PR. Okay, so TR, not very good at drawing straight lines. Sorry about that. All right, so TR and P to R. Okay, so same thing. I started with the bigger triangle, and I'm comparing it to the corresponding side length in the smaller triangle. So I did 7.5 divided by 5, and I got 1.5 again. All right. And so these numbers being the same are helping me make sure that my two triangles are indeed similar. All right. If these numbers were different, they would not be similar. And here, comparing the last set of side lengths, here RS and QR. So RS is here. Remember, starting with the bigger triangle, the measurement is 9. Comparing it to QR, the measurement is 6. 9 divided by 6 is 1.5. And so you can see when I compare each of the side lengths, the corresponding side lengths from the big one to the little triangle, I get the same number each time. This is what it means for two triangles to be proportional. In this example, we have two similar triangles, and we're going to use our similar triangles to find an unknown length. So here we have a totem pole of an unknown height. So we don't know how tall this totem pole is. We're actually going to call it X. Okay, so what we do know though is that it casts a shadow. So the sun would be somewhere up here maybe, and the totem pole is causing a shadow to produce on the ground. All right, so shadow would be here, and there's a person standing over here, and they're casting a shadow as well. All right, so we have these two shadows. And so right there, you know that when I'm talking about corresponding side lengths of the triangles, shadow matches with shadow. Okay, so let's start at the beginning. We've looked at the picture. Let's read the question all the way through. Okay, so at a certain time of day, a person who is 1.8 meters tall is casting a shadow that is 1.3 meters long. So there's their shadow, there's the height of the person. It says at the same time, the shadow of a totem pole is 6 meters long. The sun's rays intersect the ground at equal angles. So that just means that I have this 90-degree angle here, okay? And it's asking how tall is the totem pole nearest to the nearest tenth of a meter. All right, so we're comparing the height of the totem pole to the man's height over here. Okay, now we have two similar triangles, and we're going to compare. We're going to use this man's height and his shadow to figure out what X is using the shadow of the totem pole. Okay, so if I go to the next picture, I just take out the picture and remove the information. It says we're comparing the height of the totem pole with the man's height. And we're using the length of the totem pole's shadow and the length of the man's shadow. It says, let's start with what we're trying to find. We're trying to find the height of the totem pole. And so we're going to call it X, all right? And so we have X compares to 1.8. Okay, so both times I'm talking about the height, right? X compares to 1.8, and that's going to be equal to 6 divided by 1.3. Now notice both the X and the 6 come from the large triangle here, and the 1.8 and the 1.3 both come from the smaller triangle. And if you look here, the x and the 1.8 are corresponding side lengths of two similar triangles, and the 6 and the 1.3 are corresponding side lengths of similar triangles. And so I showed you this little trick in the last unit. These two things multiplied will be equal to these two things multiplied. Okay, we looked at that in the last unit, and so x times 1.3, and I can write it with the 1.3 in front because we like to have it written as a coefficient in front of the variable, is going to be equal to 6 times 1.8. And when I multiply that out, I have 1.3x is equal to 10.8. And then I divide both sides by 1.3 to isolate the x, to get the x by itself. And then I have that x is equal to 8.3 meters. Okay, so the height of the totem pole here will be 8.31 meters. It asked actually to round it to the nearest tenth, so I would change that just to 8.3 without the 1 meters. Remember, when it's asking to the nearest tenth of a meter, you should pay attention to that.